Hello and welcome to our third lecture over chapters 10.1 and 10.2, basic counting principles and permutations and combinations. Let's jump in. So first we'll start off with some definitions. A probability experiment is a process that leads to a well-defined result of all outcomes. An outcome is the result of a single trial of a probability experiment. The sample space is the set of all possible outcomes of a probability experiment, and an event is any subset of the sample space of a probability experiment. So let's do an example and discuss what these terms mean. Suppose you flip 2 coins. What are all the possible outcomes when you can flip 2 coins? Well, they could both be the same, right? So you could have both coins land on heads. You could also have both coins land on tails, right? And then you could have one of each. So you could have the first coin be heads, the second coin be tails. Similarly, you could have the first coin be tails and the second coin be heads. And now I believe we've covered all of the options. So that means our sample space is the set of all possible outcomes, right? So that gives us 2 heads, 2 tails, heads, tails, or tails. These are also all the outcomes. So each of these are possible outcomes. So an outcome can be 2 heads, 2 tails, heads, tails, or tails, heads. Now an event, let's say we want to talk about the event of having exactly 1 head and 1 tail, for example. That event would have 2 elements in its set, because we could have heads, tails, or tails, heads. So that's how events differ from outcomes. Theoretical probability is when we use assumptions in deductive reasoning process to assign probabilities to simple events. That's exactly what we just did with the coins. We assumed that the coin was fair, and when we toss it, we have a 50-50 chance of landing on either heads or tails. So the probability of an event E is going to equal number of events divided by number of outcomes. So if we used the probability of getting 1 head and 1 tail from the previous example that we just did, well, when you look up here, we had we had 1, 2, 3, 4 different outcomes, right? And 2 events. So my number of events where I get 1 head and 1 tail was 2, but my total number of outcomes for the sample space is 4. So the probability of getting 1 head and 1 tail would have been a half. Example, compute the theoretical probability of rolling the following on a single die. So the dice have 1, 2, 3, 4, 5, or 6 dots on either side on a standard die. So if we want to roll a 5, I can see that I have 6 outcomes. But if I specifically want a 5, that only occurs 1 time in this space. So we have 1 event. So the probability of rolling a 5 is equal to 1 out of 6. What about the probability of rolling a number less than 5? Well, it says specifically less than 5 and not less than or equal to. So if we want to know the probability of rolling a number less than 5, we need to see how many numbers are less than 5. So we've got 1 through 4 are all less than 5. So that means the probability of getting a number less than 5 is going to be 4 out of 6, which simplifies to 2/3. Lastly, we want to know the probability of getting an odd number. If we look at our sample space, we can see that we have 1, 2, 3 odd numbers. So the probability of rolling an odd number would be 3 out of 6, since we have 3 events out of the 6 total outcomes, which equals a half. These are some important rules about probability. So probability is never negative, and it's never greater than 1. So the probabilities always go from 0 to 1. So 0 is less than or equal to the probability of any event E. It's less than or equal to 1. When an event is impossible, its probability is 0. And when an event is certain, its probability is 1. And then the sum of all probabilities in a sample space must equal 1. For this one, let's look back at that example we did with the heads and the tails, right? We had heads, heads, tails, tails, heads, tails, tails, heads, right? The probability of flipping heads, heads, we can see is 1 event out of our 4 outcomes. The probability of getting 2 tails, we can see is 1 event out of 4 outcomes. And then the probability of getting 1 head and 1 tail, well, there are 2 places where we get 1 head and 1 tail, so that's 2 out of 4. And when you add all these up, you get 1/4 plus 1/4 plus 2/4, which is 4 out of 4, which equals 1. So that does work. So we can see that the sum of all the probabilities in our sample space does equal 1, and that's what that means. Okay. So the probability of a complement. For any event E, if E complement is the event E does not occur, then the probability of E complement is equal to 1 minus the probability of E. E complement is called the complement of E relative to its sample space. And similarly, the probability of E is 1 minus the probability of E complement. So let's say we want to use our dice example. So we want to roll a standard 6-sided die. So let's say we want to go back to, we want E to be the event that the number rolled is less than 5. Let's go back to this example. So we know that our sample space was 1, 2, 3, 4, 5, 6. And the probability that we roll a number less than 5 is 4 out of 6, which was 2/3. So then, according to our formula, P of E complement should be 1 minus 2/3, which is equal to 1/3. So let's see if this works. So if E is the event that the number rolled is less than 5, that means E complement, the complement of this event, is going to be that the number rolled is 5 or greater. So what is the probability that the number rolled is 5 or greater? Well, we look back up here at our sample space, we have 5 and we have 6. So we have 2 events out of our 6 total outcomes, which simplifies to 1/3. So you can see that we did get the same solution, both by using the formula and just by observation. Next is empirical probability. Empirical probability is based on observed frequencies. That is the number of times a particular event has occurred out of a certain number of trials. The formula is P of E equals observed frequency divided by number of trials. So let's say we're going to conduct an experiment. And we're going to flip a coin 50 times. We were going to record all of our results. And let's say we saw 21 heads and 29 tails. So then we would use this data and say the probability of flipping heads is 21 out of 50, because we observed 21 heads and we flipped a coin 50 times. So that gets us the observed frequency divided by the number of trials. Similarly, if we wanted to know the probability of flipping tails, we would say that was 29 out of 50. So typically when we're using the theoretical probability, we would say the probability of getting heads is a half, the probability of getting tails is a half, or 50-50. But in an empirical probability, you are using something you've observed from your trial to create this probability based on observed data. So that's the difference between theoretical and empirical probability. It's this observed word. Okay. The fundamental counting principle. The sequence of n procedures, if the first can occur in K1 ways, the second in K2 ways, and the third in K3 ways, and so on, then the total number of ways the sequence of procedures occur is K1 times K2 times K3, all the way down to however many Ks you have. All this is saying is, let's say, flip 3 coins. Okay? So the first coin has 2 possible outcomes, right? Heads or tails. The second also has 2 outcomes, heads or tails. And the third coin has 2 outcomes as well, heads or tails. So this is my K1, this is my K2, and this is my K3. So to figure out how many total outcomes I can have from flipping 3 coins, I'm going to do using this formula k1 times k2 times k3, which is 2 times 2 times 2, which is 8. So there are 8 total outcomes for flipping 3 coins. Okay, let's do an example using this counting principle. Suppose you are creating a 7-character password. You can choose from only lowercase letters and numbers from 0 to 9. How many password combinations are there? Well, we have 7 spots for our password. We need to figure out how many options we have for each character. So I can choose from any lowercase letter. And there are 26 of those. I can also choose from numbers 0 through 9. Well, if we're counting numbers 0 through 9, that's actually 10 numbers, because 1 through 9 are 9 numbers, and then when you count 0, that makes 10. So that means my total number of choices for this password is 26 plus 10, which is 36. 36 choices. So for each slot, I have 36 choices. Okay, and we can think of these as K1, K2, K3, K4, K5, K6, K7, per the counting theorem. And that means we're multiplying, right? So this is going to be 36 to the 7th, some very, very large number. We're going to move on to reviewing factorials. So if you haven't seen a factorial before, it's essentially just the number multiplied by every number that comes before it. So the formal definition is for any natural number n, the product of the first n natural numbers is called n factorial and is denoted by n exclamation point. So, and then these are some fun rules. So what the first one is saying is if we have something like 5 factorial, that's just going to be 5 times 4 times 3 times 2 times 1. Okay? This is a rule that you'll just need to remember. 0 factorial is always equal to 1. I don't make the rules. This is just the rule. So let's look at this bottom one. Let's say we have 6 factorial. Well, this rule is saying 6 factorial is equal to 6 times 6 minus 1 factorial, right? If I put the 6 here in this n spot, well, that's equal to 6 times 5 factorial. Is that true? Well, 5 factorial is 5 times 4 times 3 times 2 times 1. And this is in fact equal to 6 factorial because factorials are just all the numbers that come before it on a number line multiplied together. All right, let's do some practice. All right, so 7 factorial divided by 5 factorial is going to be 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 5 times 4 times 3 times 2 times 1. Well, since everything is being multiplied, we can cross out like terms. We have left over 7 times 6, which is 42. Not too bad. 10 factorial divided by 9 factorial. Well, 10 factorial is the same thing as 10 times 9 factorial by our third rule up here. Remember how we did 6 factorial is the same thing as 6 times 5 factorial? Well, now I have 9 factorial divided by 9 factorial. So this is just equal to 10. If you wanted to list them all out, I will show you that too. You can see either way we're going to get 10. All right. Next, now this one is going to be a little more difficult. You are also going to be needing a calculator. So 52 factorial divided by 47 factorial times 5 factorial. So pro tip here is whenever we're trying to simplify these factorials, you always want to pick on the bigger number in the denominator. So I want to get rid of him first, because 47 factorial is significantly larger than 5 factorial, right? 5 factorial is just 5 times 4 times 3 times 2 times 1. 47 factorial is 47 times 46 times 45 times 44 all the way down to 1. So that's a lot of numbers. So we'll try to eliminate this guy first. So this is going to be 52 times 51 times 50 all the way down to 3 times 2 times 1, right? I'm not going to list out all those numbers. That's a lot of work. On the denominator, I'll have 47 times 46 times 45, blah, 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 3 times 2 times 1. And then I'm kind of just remembering that this 5 factorial is here. I'm not really going to use him yet. But we just can't forget about him, right? So now when we're looking, we can see, well, we have this 47 in common, so you can cross him out. We have this 46 in common. We have the 45 in common. And we're also going to have every single number all the way down to 3 times 2 times 1. So we can eliminate this entire 47 factorial. What's left over is going to be 52 times 51 times 50 times 49 times 48 divided by 5 times 4 times 3 times 2 times 1. And from here, you would pull out your calculator. You would put in the numerator in your calculator parentheses around this multiplication, and then the divides bar parentheses around the multiplication of the denominator, because we want the calculator to multiply these things before it divides, right? So if you're putting all of this in your calculator at the same time, make sure you're putting parentheses around the numerator and around the denominator. But either way, once you put this in your calculator, your answer should be 2,598,960. It is a large, large number. An arrangement of indistinct objects in a specific order is called a permutation of the objects. The number of permutations on indistinct objects without repetition is nPn, which equals n factorial. So the big P denotes permutations. And then if you see the same number on either side, so if we have like 7p7, this is just saying that's equal to 7 factorial. If we have 9, choose 9, 9 factorial, etc. That's all this is saying. It's just funky notation, okay? However, if we have n objects, but we're only taking r at a time, our formula is n factorial divided by n minus r factorial. So for example, if we have 7 objects, but I only want 4 of them, that's going to be 7 factorial divided by 7 minus 4 factorial, which is equal to 7 factorial over 3 factorial. And etc. You keep solving, so. You have 7 times 6 times 5 times 4. So let's see, 42 times 20, it's what, 840, something like that. How many different ways can an organization with 20 members choose the president, a vice president, and a representative? Note that no member can hold 2 offices. So we know that this is a permutations problem. 2 things. It says no member can hold 2 offices. If we scroll up, it says distinct objects without repetition right here. So we can't repeat offices. We can't have 1 person in 2 offices. Okay? So that means we're looking at something without repetition. We also care about the order because we care who's president, we care who's vice president, right? So that's why this example is a permutations problem. We care about the order and we can't have any repetitions. Okay. We have 20 members we're choosing from. And we have 1, 2, 3 offices or positions. I'm gonna call them positions. So we have the P for permutations. We have 20 people to choose from, so that goes on this side. Out of those 20 people, we are choosing 3. Okay? So 20 people, we're gonna pick 3 of them. So I'm gonna write over here the formula. So we're gonna use this formula. So this 20 is in the in spot, so that means I'll have 20 factorial on the top divided by 20 minus 3 factorial on the bottom, which is 20 factorial divided by 17 factorial. So this is going to be 20 times 19 times 18 times 17 times 16, etc. The bottom is 17 times 16, etc. So I can cancel out the whole 17 factorial. So this is going to equal 20 times 19 times 18. This is equal to 6840. Example. A group of 5 people want to line up to take a group photo. In how many ways can the 5 people be ordered? Now this is one of those questions where order matters. No person can stand in 2 spots, right? So I've got 5 spots for my people. I've got 1, 2, 3, 4, 5, right? That they're gonna line up, they're gonna take this picture. But I can't put 1 person in 2 spots. So we're also focusing on their order. So the order matters and it can't be repeated. So that's how we know that this is a permutations problem. So out of the 5 people, I'm actually ordering all 5 of them, right? You can also think of this as if you're lining up the people, this is person 1, right? Well, I haven't assigned anybody into a spot yet for this picture. I have 5 choices for who can be standing in this spot. So then how many choices do I have to pick for person number 2? Well, since I already have 1 person standing here in this first spot, that means I only have 4 left over to choose from. For the next spot, I've already picked 2 people to stand in the previous 2 spots. That means I only have 3 people to choose from. Similarly, I'll have 2 people to choose from and then 1. And if you see here, this is the same thing as our factorial. So this is why we use factorials with permutations. And I hope that helps clarify why we do this. All right. Thank you so much for watching the video. This concludes our lecture number 3, and I hope y'all have a wonderful rest of the day.